Right. Assalamu alaikum, students. Today we are going to start with the interpretation of NMR spectra, simple proton NMR spectra. And Dr. Atya is going to explain that to you in a couple of minutes. While she is coming, we can start with watching some videos regarding the practice of proton NMR. So Fasi is going to do that.
Let's say we're given this molecular formula, C5H10O, and this proton NMR spectrum, and we're asked to determine the structure of the molecule. Let's say we're given this molecular formula, C5H10O, and this proton NMR spectrum.
Okay, so you are requested to pay full attention, and then we will solve some problems after that.
And we're asked to determine the structure of the molecule. The first thing you could do is calculate the hydrogen deficiency index. And so if we have 5 carbons here, the maximum number of hydrogens we could have is 2n plus 2, where n is equal to 5. So 2 times 5 plus 2 is equal to 12. So 12 is the maximum number of hydrogens. Here we have only 10 hydrogens, so we're missing 2 hydrogens. We're missing 1 pair of hydrogens, and so therefore the hydrogen deficiency index is equal to 1. Immediately, that makes me think about a double bond might be present in this molecule, or 1 ring. Let's go down to the integration values. So for this signal, there's an integration value of 27. For this signal, the integration value is 40.2. For this signal, it's 28.4, and for this signal, it's 42.2. Remember what you do. You divide all 4 integration values by the lowest one. So the lowest one is, of course, 27. So 27 divided by 27 is, of course, 1.
Now we don't do integration of this of the molecule in this way, as you already have seen while practicing the NMR sample running. You have seen that we usually integrate we make an intelligent guess based on the compound that we are going to run, and after that we integrate that molecule.
1. 40.2 divided by 27 is pretty close to 1.5. 28.4 divided by 27, that's pretty close to 1. And 42.2 divided by 27 is once again pretty close to 1.5. Remember, these are just the relative numbers of protons giving you these signals, but you can't have 1.5 protons giving you a signal. We need a whole number, and we need to account for 10 total protons here. So if we multiply 1...
Yeah.
You can make it full screen.
Because when I make a full screen, you will not be able to see.
Can you please insert? Add insert.
Nothing is happening.
Divided by 2 L and enter.
L, I'm doing this, but nothing is happening here.
No.
L.
Maybe
I can call the CP.
can you?
Yeah, you can.
Yes, but the same.
Oh, control enter. Okay. I did. Okay, odd.
One by 2, then we get 2 protons. So this signal represents 2 protons. If we multiply 1.5 by 2, we get 3. So this signal represents 3 protons. If we multiply...
Can you change the flyer up?
1 by 2, we get 2, and if we multiply 1.5 by 2, we get 3. So if you add all... all those up, 2 plus 3 plus 2 plus 3, that's of course 10 protons. So now we've accounted for all 10 protons using our integration values. Next, let's look at each signal one by one. So we'll start with this signal. So we have a CH2, since we have 2 protons. So this signal represents a CH2. How many neighboring protons do those CH2 protons have? All right, so we can figure that out by the number of peaks on the signal. So this signal here has 1, 2, 3 peaks. And if you think about the n+1 rule, if you have n neighbors, you get n+1 peaks. So if we have 3 peaks, all we have to do is subtract 1 to find out how many neighboring protons. So 3 minus 1 is equal to 2. So this CH2, these CH2 protons have 2 neighboring protons.
My invitation. NMR interpretation.
Practice one. You can skip that one. Practice one. Practice one is done.
Also,
From start, I'm going to create from start.
click on it.
Is calculate the hydrogen deficiency index. And so if we have 5 carbons here, the maximum number of hydrogens we could have is 2n plus 2, where n is equal to 5. So 2 times 5 plus 2 is equal to 12. So 12 is the maximum number of hydrogens. Here we have only 10 hydrogens, so we're missing 2 hydrogens. We're missing 1 pair of hydrogens, and so therefore the hydrogen deficiency index is equal to 1. Immediately, that makes me think about a double bond might be present in this molecule, or 1 ring. Let's go down to the integration values. So for this signal, there's an integration value of 27. For this signal, the integration value is 40.2. For this signal, it's 28.4, and for this signal, it's 42.2. Remember what you do. You divide all 4 integration values by the lowest one. So the lowest one is, of course, 27. So 27 divided by 27 is, of course, 1. 40.2 divided by 27 is pretty close to 1.5. 28.4 divided by 27, that's pretty close to 1. And 42.2 divided by 27 is once again pretty close to 1.5. Remember, these are just the relative numbers of protons giving you these signals, but you can't have 1.5 protons giving you a signal. We need a whole number, and we need...
Okay, so nowadays, when you run NMR spectrum, and we are using processing mostly on processing of the spectrum, and with this processing spectrum, we do not need, we usually do not have like this much number. We have to select, whenever you give sample to the NMR lab, they just have, they are technicians, right? So they are not scientists like you. So they just randomly select one of the inhibitor based on their experience of running thousands of different times, and they select that as one, and then and all the other integration depends on that particular integration that they select one. So all others are relative to that. Okay. So if you think that this is not one, maybe it's an impurity, right? But you know this. NMR people or NMR technician, they don't have such idea. So you can do it by yourself. You can get FIDs, Fourier induction filter, Fourier transform filter. And then that you can process by yourself, or you can ask them to get do not consider this peak and consider this one as one. Because in the proton NMR spectrum of a small molecule, there might most often there are some protons, because specifically we're talking about natural products. So they have stereo center. Most of the natural products that we all are working, they have some chiral centers, only more than one chiral center. And when we have chiral centers present, so each proton it behave differently. Its magnetic environment becomes different. So you can easily identify, because then we have a spectrum with one proton, at least one proton must be there. In most often in natural body. Okay, so because they always have that, except a few examples, like for example, if it's the flavon, right? Or and there is just a simple flavon, or then there might not be any chiral center there, but most of them, but most often we have chiral centers there. And if, for example, if flavon has a sugar unit attached to it, then there is a chiral center. So there are many chiral centers. So in this way, since in most of us are natural product chemicals, so there must be at least one proton. You know, you might, I'm answering the question that you might think that if there is no one proton exists in your mind, that can be, but in natural products, very, very rare. Most often in natural product chemistry, we have one proton, and most often, almost like all small molecules, we can identify one proton. And all these implications depends on your identification that you consider that one is a one proton. And then everything is effective. And we usually do not have these higher numbers. We have 1, 3, 3.1 something, 2.9 something, but we have to round this up. Definitely there is no 3.1 proton or no 2.7 proton like this. And there might be a problem in integration, number one, and number two, if you do not select the correct area for integration, or number two, there might be some impurities behind your signal that you might not be able to identify. They are in small quantity. And all impurities, since proton NMR is the most sensitive NMR technique among all NMR, because 99.998% protons are NMR active nuclei. So that is why it's very sensitive. So it means all type of the protons, if it even it's a purity, then you will be able to observe it. Okay, but maybe it's just hidden behind your peaks. Okay. What's your question? Yeah.
I'm about the chiral center. I know the formula. But my sentence, I don't know what the formula is.
Yeah.
How
Oh, okay. So that's a good question. Most often, we know the name of the plant always, right? So we know the genus and the species. If you are talking about medicine plant or any natural product, it might be marine or something. So that is why identification is critically important, because then you go to the literature and find out which type of the compounds are reported from your species and from your genus, because there are hundreds of different type of classes, but you cannot work on all these classes. You have to first figure out, most often about 99.99%, the compound that you isolate is belongs to some of the classes that already been reported. Okay, so you compare the NMR spectrum with the previous one already reported and find out something new in it, right, which is not being reported. Maybe a double bond, or maybe some additional functional group there. You know, you always have to compare with the literature. And if you identify a novel structure, that's something very interesting. Novel and new. This concept needs to be clear. Novel means the skeleton, the carbon framework is never been reported. There is some new type of the ring available that is never been reported there. So then it becomes novel, right? Otherwise, all are new. Okay, so it's not novel matter, right? Sometimes we just write, whenever we write manuscript, we just exaggerate, like it's a novel. But we have to be careful using these terms, novel and new. And new is some change in the already reported structure. Novel is something which has never been, some carbon skeleton, you know, the basic framework of a molecule is never been, then it is a novel. And to prove a novel structure, most often journals require X-ray. You have to present an X-ray on the basis of the NMR for the novel structure. Journals usually does not accept that it's a novel skeleton. You have to bring most of the cases. You have to present X-ray crystallographic structure to prove your hypothesis, right? Okay.
To account for 10 total protons here. So if we multiply 1 by 2, then we get 2 protons. So this signal represents 2 protons. If we multiply 1.5 by 2, we get 3. So this signal represents 3 protons. If we multiply 1 by 2, we get 2, and if we multiply 1.5 by 2, we get 3. So if you add all those up, 2 plus 3 plus 2 plus 3, that's of course 10 protons. So now we've accounted for all 10 protons using our integration values. Next, let's look at each signal one by one. So we'll start with this signal. So we have a CH2, since we have 2 protons. So this signal represents a CH2. How many neighboring protons do those CH2 protons have? Right, so we can figure that out by the number of peaks on the signal. So this signal here has 1, 2, 3 peaks. And if you think about the n plus 1 rule, if you have n neighbors, you get n plus 1 peaks. So if we have 3 peaks, all we have to do is subtract 1 to find out how many neighboring protons. So 3 minus 1 is equal to 2. So this CH2, these CH2 protons have 2 neighboring protons. Let's think about the chemical shift for this signal. So the chemical shift for this signal is between 2 parts per million and 2.5. And that's in the region for a proton next to a carbonyl. And that would make a lot of sense because we calculated an HDI of 1, indicating there might be a double bond present, and we need to account for an oxygen in our molecular formula. So let's go ahead and draw in a carbonyl, and these CH2 protons are next to the carbonyl. We know that because of the shift, right? The carbonyl, the oxygen de-shields these 2 protons a little bit and gives us a higher value for the chemical shift compared to something in an alkane type region. All right, let's color these protons in here magenta. So we're saying this signal is due to those 2 protons. Let's move on to the next signal. So we have 3 protons, so that would be a methyl group, so CH3. How many neighboring protons for those methyl protons? Well, there's only 1 peak here, so 1 minus 1 is 0, so 0 neighboring protons. What about the chemical shift? So the chemical shift for this signal is once again past 2 parts per million. So this signal is de-shielded, right? So these protons must be de-shielded a little bit, and those must be next to our carbonyl. So we'll draw in our methyl protons, right, being de-shielded because they're next to the carbonyl. And let's make these blue. So these protons in blue here, these 3 protons are giving us this signal, and we should expect 0 neighboring protons. Right? So those protons are on this carbon, and the next door carbon has no protons on it. So 0 neighboring protons makes sense. Move on to the next signal. So this signal represents 2 protons, so that's a CH2. How many neighboring protons? Right? Well, let's count up how many peaks we have. 1, 2, 3, 4, 5, 6. So 6 peaks, so we subtract 1 from that, so 6 minus 1 is 5, so we would expect 5 neighboring protons. Let's move on to the next signal. 3 protons, right, so that's a methyl group, so CH3. How many neighbors? Well, we have 1, 2, 3 peaks, so 3 minus 1 is 2, so we would expect 2 neighboring protons. Now these 2 signals, right, this signal here and this signal here, we're talking about under 2 parts per million now. So these must be the furthest away from the carbonyl, right? So they're not being de-shielded as much as the 2 signals in this direction. So these 2 neighboring protons for the methyl group must be these 2 protons right here. So let's go ahead and draw that in. So we have our methyl protons right here. And let me make these protons red. So these protons right here in red are giving us this signal. And from the signal, we know that these methyl protons are next to 2 neighbors. And so we must have a CH2. We must have a CH2 next to that methyl. And so let's go ahead and draw in our CH2. And this CH2 must be this signal right here. All right, so let's think about how many neighbors. We expected 5 neighbors for these CH2 protons. Let's count them up. 1, 2, 3, 4, 5. So 5 neighboring protons matches what we see on the NMR spectrum. Now, those protons, those magenta and red protons, are actually in different environments. And so the simplified version of the n+1 rule isn't quite true, but it works for this example. It works for this example, so we're going to go with it because all we care about is getting the structure of our molecule here. All right, so let's think about the red protons again, right? So the red protons are supposed to have 2 neighbors. So how many neighbors do the red protons have? Here's 1 and here's 2. So this makes sense. So that one makes sense. This one makes sense right here. We just talked about that. Let's think about the magenta protons. So the magenta protons were supposed to have 2 neighbors. So let's look at the carbon next door to this one. So here's the carbon next door. Here we have a neighbor, and here we have a neighbor. So this makes sense. And then we already talked about the blue protons, right, having 0 neighbors. So everything seems to make sense here. And to sum everything up, make sure to count all of your atoms, and you will get, of course, 5 carbons, 10 hydrogens, and 1 oxygen when you do that. So this is the dot structure that we were trying to find. Let's take a look at another one here. So we have a molecular formula of C8H10, and let's go ahead and calculate the hydrogen deficiency index. So if we have 8 carbons...
Take the hydrogen deficiency by yourself. Hydrogen deficiency index.
Oh. Wait.
Everyone calculated?
Yes.
Okay. Yeah.
Then we can have a maximum of 2 times 8 plus 2 hydrogens. So 2 times 8 is 16 plus 2 is 18. So for 8 carbons, 18 hydrogens is the max. Here we have 10 hydrogens. So we're missing 8 hydrogens, or we're missing 4 pairs of hydrogens. So the hydrogen deficiency index is equal to 4. Remember, anytime your HDI is equal to 4, you should think about a benzene ring. So I'm going to go ahead and draw a benzene ring in here. And let's look.
Okay, so now whenever it's sometimes we do not always need to calculate using the formula. Looking at this structure, we can already immediately tell how much the hydrogen deficient is. For example, this is aromatic ring with 3
double fold.
double bonds. So 3 plus 1 for ring. So whenever there is a ring, so there is 1 you need to add. So you all the time, you do not need to calculate with the formula. You can just looking at the structure. Most often when we report hydrogen deficiency index, we just calculate at the end when we already got the structure, right? So we already got the structure and we are just writing the manuscript and then we calculate at that time. So that's the usual all natural product chemistry. So looking at this structure, we do not need to go back and calculate the formula. We can immediately look at the structure. So whenever there is a ring, there is 1 hydrogen and the number of double bonds there.
Look at the integration. Right, so sometimes you'll see the integration given like this. So this represents 5 protons for this very complex looking signal right here. This signal over here represents 2 protons, and this signal represents 3 protons. So let's go back to these 5 protons with this complex signal, right? This is in the aromatic range, right? So approximately 6.5 to 8. Those must be 5 aromatic protons. So we can.
I would like you guys to make a coupling tree. Up to print it now in your notebook. Coupling tree. You know how the doublet are formed, how the thread are formed.
I know it.
You know this?
How for example, how the second tree came quartet and
Yes,
uh,
yes.
I know it.
Yeah.
That's what I want to explain.
So can you, every one of you, can you make on your notebook a coupling tree? No? You don't know how to do it? How the triplet are formed,
Do the same. what
how
you-
the peak is being divided into doublet or triplet. How would you do it? The most simple and just one rule. I'm not talking about double doublet or some complex structure like triplet of doublet of triplet or something, not complex. Just the simple and plus one. Yeah. On your notebook. Only one person number. Well, so, okay, so then I think I would explain first, and then you will just. Okay. Um, Right, looking at this structure. Okay, for example, whenever you have a peak, so the peak is 1. I drawing not for the before this. So the whenever you get something, you always need the same peak. For example, whatever the peak you have in your hand, like 1 centimeter, 1 or whatever. Right, so you need to have the same distance. This peak is divided in that is doublet. This one is single. Right, for example, suppose this is when we are making on our notebook, so we should have some scale, so everything should be perfect. For example, if I consider this one, as 1. So all the lines have to be 1 each. Okay. Then this P. And so now this is, if you look at the intensity, this is 1, right? And the doublet has 1 and 1. So means this is singlet and doublet means that equal intensity, right? What about this triplet? 1, this is 1. Okay, so 1 is coming from here to 1. And 1 is coming from this one is 1 here. Right, 1 is here and this one is here. So 1 is to 2 is to 1, right? Then the triplet will be 1 is to 2 is to 1. Okay? So that will proceed further. If you have the quartet, then so here 1, right? And here this is 1, 1 means it was already 2. So 2 and 1 from here, 2 from here. 2 from here, 1 from here, 1. So 1 is to 3 is to 3 is to 1. So the peak will be 1, 3 time intensity of this one, 3 time intensity of this one, and then 1. So that is 4. Okay. So that is proceed further. So can you make next? Yeah.
First to square first to square.
I'm not ready.
Using mathematics pressure, the first to square.
Yeah, yeah. You could. It's just for you guys to understand how they are, like why is 1:1 ratio of a doublet and why triplet is 1:2. Yeah, 1:2:1 is a triplet and quartet 1:3:1.
Go ahead and draw in five protons off of our benzene ring. So even though those protons are in slightly different environments, right, because this integration value is 5 here, and we know a benzene ring is present, we're done, right? We don't have to worry about the slightly different environments. We know that these 5 protons are giving us this complicated signal over here. All right, next, let's look at this signal. So 2 protons, so that must be a CH2. How many neighboring protons for the CH2? Well, there's 1, 2, 3, 4 peaks. So if there's 4 peaks, 4 minus 1 is 3. So these CH2 protons have 3 neighbors. All right, let's look at this next signal. So 3 protons. So this must be a CH3. How many neighboring protons do we have for the CH3 protons? Well, we have 1, 2, 3 peaks. So 3 peaks, 3 minus 1 is 2. So 2 neighbors. And so 2 neighboring protons, that must be these 2 neighboring protons. And so we can go ahead and draw an ethyl group, right? So this is an ethyl group pattern over here. So there's a CH2 and there's your CH3. So let's draw in all of our protons. So we have these protons and we have these protons. And let's color coordinate here just to make sure everything makes sense. So these red protons right here, they must be giving us this signal. So these methyl protons, right? We'd expect 2 neighbors because we have 3 peaks on our signal. And here are the 2 neighbors, 1, 2. So 2 neighboring protons. Let's look at these 2 protons next. So these 2 protons are giving us this signal. We would expect 3 neighbors because we had 4 peaks, 1, 2, 3, 4. So 3 neighbors, so here's a next door carbon, so 1, 2, 3, 3 protons, and then this is also a next door carbon, but there are no protons on this carbon. And so we see only these 3 neighbors, and so everything seems to make sense. And once again, count up all of your atoms and make sure you've accounted for everything. For example, right, you have 8 carbons you have to worry about. So on your ring we know there are 6. 1, 2, 3, 4, 5, 6. And then we get 7, and then we get 8. So the 8 carbons is correct. And then if we count all those up, we have our 10 hydrogens accounted for too. So this is the NMR spectrum for ethyl benzene, right? And this one was a little bit easier than the previous example.
Yeah.
Can you put in?
Yes, the first one.
These red protons right here.
Stage 2. We have 4 peaks. How do you make it stage 2, not stage 4? Why do you we have 4 peaks here.
4 peaks here.
Yeah, but we couldn't stage.
Yeah.
But why is that stage 3? Okay, we have 3 here. 5. 5. That's
Okay, so this is a splitting pattern.
Hmm.
Splitting pattern, the simplest one in NMR is n plus 1 rule. Okay, so n means the number of protons. Okay, this do not consider any number of protons. Okay, and n plus 1. If there is 2 protons, so n is 2. So 2 plus 1 is 3. So splitting pattern depends on the number of neighboring protons. Okay. So and is the number of proton in your neighbor, in next door. Okay. So and just ignore this one. Do not look at it. Okay, just look at me. You have 2 proton in your neighbor, right? So as per the simplest rule, so this because of the neighboring proton, for example, there are 2 protons here sitting with you, Adil and Mahmood, right? So Adil and Mahmood are your neighboring protons living together in one home. Okay, so because of that, you will split into how many signals? N plus 1. These are n. N are 2. So 2 plus 1, how much? 3. So you will split into 3. Okay, because of this is the effect of your neighboring proton. Okay, and so it means when you let's think about this CH3. Okay, so now you are a CH3. Okay, and in your neighbor, Adil and Mahmood are the 2 protons of CH2. Okay, because of this CH2, you as a CH3 will split into 3. Means 3, where in the Pascal triangle there is 3? Triplet, right? Okay, and if there are 3 protons in your neighbor, what's your name? Aisha. Okay, so in Aisha's neighbor, you 3 are living together in one home. Okay, and you are protons of 3 different protons, 3 protons of CH. So n plus 1. So 3 plus 1 is 4. So Aisha will split into quartet, 4 signal. 1 peak is split into 4 signal. And this splitting pattern actually just shows the number of neighboring protons. Okay, and it doesn't mean how many protons you have. You are itself. Okay, what's your name? I don't know your name. Hani. Okay, but honey. Alright, so honey, you need to just consider that because
In the previous example, we, according to the number of pixels, it is
here also we are just looking at the simplest example. These are all n+1 rule. There is no complicated signal like doublet of a doublet or triple D or doublet of a triplet or TD pattern, whatever. There are no such kind of complicated signaling. These are the most simple, easiest NMR. Okay, can we move further, Hani?
Okay. How we directly go to 263 and
Directly go means.
see the first example. Previous one. We directly after hitting the fix, we have 683. We have 2 fix.
Okay, for example, just consider you do not know the structure and you have this simplest spectrum in front of you. So when you see the triplet, then you immediately think there must be a CH2 besides in the next door of this triplet. Okay? And intensity, looking at the intensity, you know there are 3 protons. Okay? So 3 protons, you know that this triplet is 3 proton because of the intensity, the integration value. That's why integration is important. That's why I told you in the previous example that NMR people are technicians. They just do it by their experience of thousands of NMR they have done, but they are not sure. Okay, so except Abdul Mateen, because he has done absolute. So all others are technicians. So they do things as per their experience. But you know your compound very well. You know from which plant, which species, which genus you are working and isolating these compounds. So you have some idea of type of the skeleton and type of the spectrum that you are expecting, right? And then you can looking at this because you have some concept, some knowledge of the previous literature. You can decide if they consider something as a 1 proton and you think it's not the 1 proton, maybe an impurity. Maybe they consider sometimes they consider like silica peak. Sometimes, when you isolate a compound using methanol and silica, then you could see the signal of silica as well. And then sometimes they also integrate that, so that you should know as a scientist that what need to be considered and what not considered. Okay, so whenever you have this spectrum, so looking at the triplet, this is the 3 proton. From the integration, this. Integration is first thing, while processing you have done. So these are the 3 protons, a triplet. But triplet means this signal is triplet because of n+1 rule. So triplet means it has the 2 protons besides it. So 2 + 1, that is why is 3. And when you see a quartet and you see there are integration are the 2 protons. And the 2 protons and it's a quartet. So it means n+1 rule. So 3 + 1, 4. So that's why 4 signals you are observing. Okay, so besides this CH2, there is a CH3. And when you see this multiplet, so they all are these are multiplets. And looking at the integration, you know there are 5 protons, and the value lies in the aromatic region, right? More between 6 to 8, it's an aromatic. So all these proton lies in the aromatic region, and there are only 5 protons. So you expect, okay, they are all together. That's why, and there is no substituent in between. Otherwise, you can exactly see a doublet of orthocoupling proton or meta-coupled proton. Right now, you have 5 protons. And if you see, all these protons are either orthocoupled with each other or meta-coupled with each other. So coupling is there, but there is no substituent in between. So definitely they appears as a multiplet. Because all these orthocouples, you understand orthocouple, right? The 2 protons in adjacent carbon, vicinal carbon. So
You go there. I think, there's a way.
why 3? Because integration, you already know the integration.
Each proton has the ring. How many?
Integration. The number of protons are there. Looking at the integration.
Proton 41 the ring. How many protons?
Then I understand your question. You are saying that the 2 orthoprotons should appear at the same position, and I'm talking about the substituent. With reference to the substituent, the 2 orthoprotons should appear at same position. 2 metaprotons should appear at the same position, and paraprotons should appear at one different. But the problem is, your question is right, but you can see all these when there is a substituent there. For example, okay, for example, right now, so right now, you could see that you are thinking this is the substituent. This should appear at one, and this should appear at one, and this should separately, right? But that your question is absolutely right, but you can observe only, for example, if there is no H here, if for example, there is a substituent OH, okay, then you exactly see what you are saying. Okay, so you see these 2 protons together at one position, but integration is there. So you know there are 2 protons. Integration and chemical shape, they are 2 different things, right? So, for example, if you have OH group here or any other substituent is here, so these 2 protons appear at one position, exactly same chemical shape. For example, if they appear 6.8, so this will also appear at 6.8. Okay, and if this appear at 7, so this will also appear at 7 if there is a substituent there. But since there is no substituent, so right now in the current condition, this proton is a orthocouple to this and metacouple to this, right? Orthocoupling and metacoupling. Orthocoupling and metacoupling. So each proton is orthocoupled and metacoupled with the other one. Okay, so that is why it appears as a multiplet, but the integration is there. So 5 proton, you know there is a 5 proton. And if you do not place these 5 proton here, where would you place? There is no other place. Okay, you have 5 aromatic protons that are multiplet. Okay.
But we need to think about, here we have a proton NMR NMR spectrum for a molecule that has a molecular formula of C5H10O2. And let's start by calculating the hydrogen deficiency index. So if we have 5 carbons, we can have a maximum of 2 times 5 plus 2 hydrogens. And so that's equal to 12. So 12 hydrogens is the maximum number for 5 carbons. Here we have only 10 hydrogens. And so we're missing 2 hydrogens. We're missing 1 pair of hydrogens. So therefore, we can say the HDI is equal to 1. And when the HDI is equal to 1, I immediately think a double bond is present in this molecule or a ring is present in this molecule. Next, you go to the integration values. So for this signal, an integration value of 33.2. For this one, 48.4. For this one, 33.3. And then 48.7. And you divide all 4 integration values by the lowest one. So the lowest one would be 33.2. So 33.2 divided by 33.2 is obviously equal to 1. 48.4 divided by 33.2 is approximately 1.5. 33.3 divided by 33.2 is obviously very close to 1. And then finally, 48.7 divided by 33.2 gives us approximately 1.5. And these numbers tell us the relative ratio of protons that are giving us these 4 signals. But we need to think about 10 protons, right? So we have 10 hydrogens here. And so this is only relative. To get the absolute number of hydrogens, we need to multiply these numbers in this ratio by 2. If we multiply 1 by 2, we obviously get 2. So this signal represents 2 protons. Multiply 1.5 by 2 and we get 3. So this signal represents 3 protons. Multiply 1 by 2, this signal is 2 protons. Multiply 1.5 by 2, this signal is 3 protons. All right, let's go through and look at each signal one by one. We start with the signal that has 2 protons on the left over here. So 2 protons, so we're talking about a CH2 group. So I go ahead and draw in a CH2 group over here. How many neighboring protons for this CH2 group? We can find that by thinking about the n+1 rule. If we have n neighboring protons, we would expect to see n+1 peaks. So how many peaks do we have? 1, 2, 3. So 3 peaks. So to find the number of neighbors, just subtract 1. So 3.
Okay, so now you know this spectrum, looking at the spectrum, okay? So this is number of protons are 3. The red color are the number of protons which comes from integration values, okay? The intensity. And integration also mentioned on the back side of your proton NMR spectrum. So you can also exact number that you can calculate also. Okay, so here there are 2 protons and it's a triplet. So what does this mean? We are talking about the proton resonating at 4 ppm. It's a 2 proton and it's a triplet. So 2 protons means it's a CH2. But triplet neighboring also has 2 neighbor. Exactly. Okay, so and what about the signal as at 2 ppm? Is a singlet. 3 protons, no neighbor. So no neighbor means it has some heteroatom attached to it. Okay. And CH3 might be 3 protons means CH3, and it's very downfield for the CH3. You know, CH3 usually appears around 0.9 to 1 or 1.1 ppm, and this is 2 ppm. So that actually the downfield shift of this CH3 represent there is some heteroatom and some more electronegative atom. Okay, and what about the signal around 1.6 ppm?
It's a 2 proton. Okay. And hmm? So, okay, we will discuss this later at the end. First, go to a proton at 1 ppm. These are 3 protons. 2 neighbor. Okay, looking at this, I request Hani to come forward to the board and draw whatever the constituent you are observing. Yeah.
Before I did it, actually, I was something.
No, we will discuss. We are here. We are not
just,
doing further.
yeah, before he goes, as I need to know from where comes to see this from integrated.
Integration.
Yeah, I lost it. How, there is two protons in.
From the integration.
Uh-huh.
When you get the spectrum, when you are processing that spectrum, as I mentioned you have to consider something 1 proton, 2 proton based on your literature, experience, reported from. So you consider this. These are all relative to what you consider as 1 proton. You have to assign either 1 proton, 2 proton. The first you need to assign. Then computer automatically integrate the other. Okay, so that is all related. Yes. No, on this one. Just write it down. Okay. Okay, you are allowed to help Hani. Okay?
Let's talk about the switch to here.
Yeah, you first.
And then we move the and here message 3. Into it. We have health.
Yes, that's
And
Is he right so far?
Yes.
it's correct.
So you all need to involve here. Okay.
Correct. Now it's going Now it's going with how to arrange.
Okay.
Okay, now we have also either.
Now you need to
double
join.
bond or ring here. And we have also then.
Why you are having ring right now? Tell
We
me.
have either. Either this one.
Okay, options, yeah.
And we have also here. And we can think about double bond. And we have ring 0 here. And thinking about double bond.
put it in the corner,
Yes.
Yeah.
right?
You can also go ahead.
Not like
Whoever would like to help Hani can go forward.
I need that.
And we can think and then 0 here. That is isolated from.
From the rest. Okay. Good.
Or we have. No. Yes, yeah. Okay. No. There or there? There. Right. What?
No, maybe because I have it.
Maybe there or there. Actually, they will help you. We were 5, okay. And we'll.
Replace the place of oxygen.
What about?
Yeah,
This is
maybe
a
it's
correct-
better.
Okay, very good, honey. Okay,
Second one.
now, okay, honey, can you please explain to all of us why you assigned, how did you come up to this, either of these or both these structures? We are waiting.
How you know?
The difference, the difference in chemical shape of CH3 attached to carbonate.
Ali, because okay, who said the first one is correct? As your hand. Who said the second one is correct? Yeah, you had them going.
We agree to both. All right, very good, honey. So you understand and you everything, almost everything. So except
what
you
the
need to
correct one?
understand this because of the electronegativity and the presence of a double bond of the neighboring atom, you have to think about the what would be the chemical shift and what would be the effect if there is an oxygen attached to it, or if if there is a direct oxygen attached to it, then there is more oxygen has a lone pair of electrons. That is like more electron, it's an electronegativity and the lone pair of electrons. So both. So you are going to observe both effects. And when you have the carbonyl directly attached to CH3, then it's more like electron withdrawing effect. Okay, because of the carbonyl. Okay, so we'll play the video now and see what they come up. Oh, you don't understand? No, ma'am, because me. Okay, now you need to come there. And Hani, please go there. You also go there. Hani will explain you. Please come. Today we will not move further. First, you need to understand why Hani has drawn these two structures. Okay, ask your question from Hani and Hani will explain. Speak loudly. We cannot hear you, please. Take this mic. Please take this.
Okay.
Okay, I want to ask that if there is no material. The carbon here, it doesn't have it doesn't have it has paper here like 5 and 0 and D. I don't understand the sequence whether this one is correct and whether this one is correct.
If we haven't decided which one is correct yet.
So how can I decide that either I have to draw this one or that one?
This is what I'm saying. Either one of them, the oxygen is here and there. We haven't decided yet. Okay, but the rest you understood. Or you do not, okay.
Oh no, I don't understand.
Okay, speak then.
Can you just draw once more so I can understand this, how to draw this?
Okay, Yohani, you need to explain now.
Dr. Hans,
Yeah.
I will answer to you.
No, you have to answer to her.
Then sometimes
Yeah.
explain, and I come and answer. Okay.
Yeah. Please, please. And honey, you need to observe whatever he's saying is right or not.
Thank you.
Okay.
He said there is a free proton that has no neighbor. It means you can put your carbon atom having no neighbor means there's a carbon next to another carbon, or an heteroatom that is carrying. Okay, now we have two proton triplets. You can put it in two proton. Triplet means there can be a free proton neighbor. Sorry, two neighbors. Yeah, two neighbors. Then we have three proton singlets. Three proton singlets can be CH3 next to a carbon, and we have one hydrogen deficiency, so can be a carbonide. And we have one more oxygen, then we can think of an ester. Yes, it can be like this, or CH3, or C, because of the two oxygen atoms. So we've been able to talk about three proton singlets. We have two proton sextets, which is like CH2 surrounded by by 5. Now, if we have it like this, 2 here, meaning 4. It means we have a CH3 and a CH2. So from where we were coming, we have one CH2. This can be part of it. Then there's another CH3 triplet, meaning this. So we've been able to account for 3 carbon atoms out of 5. That is CH3, CH2, CH2. Now remaining the 2 carbon atoms and 2 oxygen. So we can now come back here. Which one will fit in? Either this or this. So now the reason, okay, should I say which is the reason why this is the correct is the more correct is because the 2 proton triplets at chemical shift 4 is highly shielded because of this. So this is more.
What's your name?
Akishola.
Aki. Okay. Thank you so much, Akishola. Yeah.
Minus 1 is 2.
I
So
think we can
these
start
two CH2 protons have 2 neighboring protons. Next, let's think about the chemical shift. So this signal has a chemical shift of approximately 4 parts per million.
Okay.
And that's the two CH2 protons have 2 neighboring protons. Next, let's think about the chemical shift. So this signal has a chemical shift of approximately 4 parts per million. And that's the highest value for the chemical shift out of all 4 of these signals. And that's the region for a proton that's connected to a carbon that's bonded to an electronegative atom. And if we look at our molecular formula, right, we have 2 oxygens here. So I'm going to take one of those oxygens and put that oxygen on that carbon, because once again, when you're thinking about the signal for a proton on a carbon that's bonded to an electronegative atom, you get a chemical shift somewhere, in this case, close to 4 parts per million, because the oxygen is de-shielding those protons, right? The oxygen is withdrawing electron density. All right, so that's one piece of the puzzle, and let's move on to our next signal. So this will be the next piece of the puzzle. We have 3 protons, so that's a methyl group. So let me go ahead and draw in a methyl group here, so CH3. How many neighboring protons for those methyl protons? Well, we see 1 peak here. So 1 minus 1 is 0, so 0 neighboring protons. Let's think about the chemical shift, right? So the chemical shift is just past 2 parts per million, and that's in the region for a proton that's next to a carbonyl. All right, so let's go ahead and draw in a carbonyl here, and we're assuming that the carbonyl carbon is bonded to another carbon over here. That makes sense in terms of numbers of neighbors. Right, so let's use blue for this, right? So the signal for these 3 protons, right, 0 neighbors. And so if we go to this carbon, right, if there's a carbon over here, there are no protons on this carbonyl carbon, and so that explains this piece of the puzzle. Next signal, a CH2, right? So we draw in a CH2 here. How many neighbors? A little bit hard to see. 1, 2, 3, 4, 5, 6 peaks. 6 minus 1 is 5, so we would expect 5 neighbors using the oversimplified n+1 rule, and we'll come back to that CH2. And finally, we have a signal with 3 protons, so a CH3. How many neighbors for these methyl protons? Well, we have 1, 2, 3 peaks, so 3 minus 1 is 2, so 2 neighbors. All right, let's put all of the pieces of the puzzle together, and let's draw the final dot structure. So let's start with this piece of the puzzle right here. So we have a carbonyl, so I'm going to draw in my carbonyl here, and then we have a methyl group bonded to that carbonyl. So I'm going to draw in our methyl group like that, and we used blue for these methyl protons. So the signal for these methyl protons appears right here. Next, let's think about a possible functional group, right? Well, we have a carbonyl, and then over here, right, we have an oxygen. So if we put the oxygen next to the carbonyl, that gives us an ester. So let's go ahead and do that. Let's put the oxygen next to the carbonyl, and then bonded to that oxygen, we had a CH2. So I draw on my CH2 there, and let's identify those protons. So the protons in magenta are giving us this signal over here. All right, next, let's use red, and let's think about these protons, these methyl protons right here. Those methyl protons have 2 neighbors, and it makes sense that they would be these 2 neighbors right here. Right, so these chemical shifts are under 2, so those are relatively far away from the oxygens. So let's draw in the methyl protons next. So we have our methyl protons right here, and let's make them red. So let's highlight those. So these methyl protons right here are giving us this signal. And then finally, we have a CH2 left right here. So we draw in our CH2, and let's make these green. Right? So these 2 protons right here in green are giving us this signal. All right, let's go through and see if everything makes sense, and we'll start with the green protons. So we predicted 5 neighbors, right? So we look at the carbon that the green protons are on, we go to the next door carbon, 1, 2, 3 neighboring protons. We go to the other next door carbon, 1, 2, so a total of 5 neighbors, and so that's what we predicted using the n+1 rule. In reality, the magenta and red protons are in different environments, and so this oversimplified n+1 rule isn't exactly correct, but it corresponds to what we see on the NMR spectrum. So we can just go with it here. It helped us figure out the structure of the molecule. All right, so this makes sense. 5 neighbors here. Let's move on to the red protons. We predicted 2 neighbors for the red protons, so we go to the carbon that's next door, right? So this carbon has the red protons. We go to the next door carbon, and we see 2 neighbors. So this makes sense. All right, let's look at the magenta protons, right? So the magenta protons, we predicted 2 neighbors. So the magenta protons are on this carbon. We go to the carbon next door, and I see 1, 2 neighbors. So this makes sense. And then finally, the blue protons over here, we predicted 0 neighbors. So we go to the carbon that's next door to this carbon, and there are no protons on this carbon, right? So 0 neighbors, and that's why we got our singlet over here. So this makes sense, right? The chemical shifts make sense, the splitting makes sense, everything seems to make sense for this ester. One thing I've noticed when students get a problem with an ester, sometimes they reverse the ester. Let me show you what I mean. So I've seen a lot of students do this on exams. What they'll do is they identify the fact they have an ester, but in this case they would put like the methyl group on the oxygen and then draw in the rest of the molecule over here. So we had 3 carbons, so 1, 2, 3. And they'll put this down for their answer on the test. So why is this wrong? Well, this is wrong because the signal for these methyl protons, right, that's right next to this oxygen is de-shielding. So we would get a singlet for these methyl protons, but the signal would be closer to 4 parts per million and not right here at 2 parts per million. And so that's a clue as to how to assemble the pieces for an ester. So think about what's next to this oxygen here. Think about the chemical shifts, and you won't make that mistake. For this NMR spectrum, our molecule has a molecular formula of C4H10O. And let's calculate the hydrogen deficiency.
So we'll stop it here, and as now you understand, so you guys are not the only one. All students always puzzled about the placement of either the methyl group or CH2, either with the carbonyl or oxygen, and it depends on the chemical shift. So if you, I would recommend there is a table for proton NMR chemical shift, not the table, a picture, a range where the chemical shift of different groups are mentioned. In the book of NMR spectroscopy of Professor Iqbal Chaudhary and Professor Daur Rahman. So just have a look on these. This is a nice picture that it's always helpful. Because when you're assigning, so there are multiple factors that you assign for one particular structure, but in general, just to have some idea that where these kind of the proton around which functional group it should resonate. So you should I would recommend to memorize these chemical shifts, because this is the first clue that you get. Other than the splitting pattern, where this particular proton should appear, what is the range. So if you can memorize, I think maybe in the next class, we will show you the image and also share with you. And then I think there is similar kind of table and the image for the C13 NMR. So I would, in next class, we will share with you so that you guys kind of memorize. When you practice, then you just, but when you are a beginner, whenever you are a beginner, so then you need to memorize, or at least you should have the table. So where this kind of the proton should, then we will share that with you in the next class. So, and next 3 classes would be the last classes that will be taken by Professor Iqbal. He is coming back to Karachi today evening, and from Monday, Tuesday, Wednesday, he will take the class. So I will recommend all of you to attend this class, and because this will wrap up the whole course. These will be the last 3 classes. All right. Thank you. That is. Yes.
But
I may always have a question. So, welcome.
the video is recording is available on the website. That's the safety.
What
And
you
you want
want,
ID to upload then.
okay, send the link. Okay, we'll share the
I have
link.
seen the link that is in the time, but for all details, all the action. Then it should be 2 weeks or 3 weeks not available.
Oh, okay, okay, I will ask. Thank you for mentioning.
Thank you.
Yeah.